So first, I want to thank all of you for joining us this afternoon to talk about the Midrich Challenge, our second challenge that we've held through Midrich. It's the mRALE Mastermind Grand Challenge. And on behalf of myself, I'm Sam Ramato and Karen Drucker and Lumir Hajitsky. We are co-directing the challenge efforts within Midrich. Also want to acknowledge Emily Townley, who organized this call and has been an amazing project manager for all of the Midrich activities involving challenges and beyond, and Ben Bierce, whose platform was instrumental in making this challenge possible. And of course, we are working on behalf of the Midrich Grand Challenge Working Group, a large collection of experts from across the country and across a wide range of domains that make these challenges both clinically relevant and technically feasible. So as you all probably know, this is an effort through Midrich, the aim of which is to foster machine learning innovation through data sharing for rapid and flexible collection, analysis, and dissemination of imaging and associated clinical data by providing researchers with unparalleled resources in the fight against COVID-19. So all that means is go to midrich.org or data.midrich.org, and you will see a very large collection of publicly available images that have been collected over the past 3 years that are all designed to be properly curated with issues of bias being maintained and controlled, and other technical aspects of the images that are being used for the medical imaging research community to specifically look into COVID in a way that is unparalleled as far as the resource and the magnitude that's available to all of us doing this kind of research. The task for this specific challenge, the second, as I mentioned, is to compute automatically through AI techniques an mRALE score for chest radiographs. And mRALE is the modified radiographic assessment of lung edema. And taking this example image here, what is done is both for right and left lungs, there is a score assigned by a radiologist of the extent of disease in each lung and then the density of the disease present, if any, in each lung. And that is going to end up with the score on the range of 0 to 24, which is the sum of two products, the right lung extent times right lung density and the left lung extent times left lung density. And so we had, using this interface through MDAI, we had 22 annotators that collectively provided a single mRALE score for over 2,000 training and validation cases. And we had 3 of these annotators each evaluate and assess an mRALE score for 814 test cases. So the test cases were triply annotated for increased robustness, while the training cases, much larger in number, only had a single score from among our annotators. The purpose of the challenge itself was then to have groups develop an AI system that assigns an mRALE score to these chest radiographs. We use the Midrich platform that Ben is responsible for, and we use as the performance assessment metric the weighted quadratic kappa with the reference mRALE scores provided by our annotators. This is an interesting challenge from Midrich's perspective. We had a larger group of cash prizes than ever before. We had a first place prize of $15,000, all the way down to $5,000 for the 4th through 7th places. And perhaps even more significantly is through the Midrich resources and our connections with the FDA, we were able to offer support in the 1st and 2nd place teams in taking their models through the FDA regulatory process if they chose to pursue that approach. So what's happening today at this webinar is we will hear from the top 3 teams, all of which were actually individuals, Ian Pan in 1st place, Ron Zhang in 2nd place, and Finn Barrett in 3rd place. And we will hear from them with regard to the methods they developed and how they achieved their successful performances. So with that, I will stop and turn this over to Ian.
All right, thank you very much. I'm just going to go ahead and share my slides. Okay, I believe they are showing up now.
Yes, you're good.
Okay. So my name is Ian. I'm currently a radiology resident at Brigham and Women's Hospital, and I'm going to be presenting my 1st place solution to this challenge. And I'd just like to start off by thanking the organizers and all the annotators for helping put this together. This is just a brief summary of what I did for this challenge. So first, I cleaned the data a little bit because some of the studies had multiple radiographs, but they were all pretty similar. And so I just picked the best one if there were multiple based on my own assessment of the images. I predicted the extent and density for each side, as opposed to trying to predict the mRALE score directly. I also trained a model to crop the right and left lungs from the whole image, and then train models on both full images as well as crop lungs and put them together in an ensemble for the final solution. Just going over the data briefly, so there were close to 2,600 radiographs from just over 2,000 studies with density and extent for each lung. So I looked at all of the studies where there was more than one radiograph and then selected the best image based on my assessment of what the contrast looked like and how much of the lungs the image actually covered. So basically reduced the data set to 2,079 radiographs. And then I also manually annotated about 1,000 images with bounding boxes for the right and left lungs as part of one of the models that I trained as well. This really didn't take that long, probably only an hour or so. The other data set I used was the RSNA pneumonia detection challenge data set. This was from, I think, 2018, hosted on Kaggle. And this contains over 26,000 radiographs and also bounding boxes around the opacities if the radiograph contained one, which I didn't use specifically for this challenge. But there were 3 classification labels that came with these radiographs that I did use to pre-train my models on. So briefly, the training process involves first pre-training the models on the RSNA data set using just basic classification task, and then fine-tuning on the competition data set. I used 2 main architectures, the original efficient net architecture as well as the newer CompNext architecture. Both are convolutional neural networks. For the loss function, I treated the problem as a regression task. So you could think of it one way as a classification task, since we have discrete classes for density and extent, or you could treat it as a regression task because there's some sort of ordering to the labels where 0 is nothing, 1 is a little bit more than that, and 2 is a little bit more than that, etc. And so I combined mean squared error and then mean absolute losses for the loss function. And then for the whole image models, I trained using 4 labels, density and extent for each side. And then for the crop lung models, I trained using just 2 labels. So these models were agnostic to the lungs themselves or the laterality of the lung. So basically, right lung would have 2 labels, left lung would have 2 labels, and these were essentially treated as individual images during the training process, which effectively doubled the number of images that I was using when I was training these models. And then for cropping the lungs, I used an efficient net model, treated it as a regression task with 8 labels, just specifying the coordinates for the bounding boxes for each side. This is just a schematic for the inference pipeline once the models were trained. So you can see I have a whole chest radiograph here. And then at the top, it goes through the model that crops the lung. So I have right lung, then left lung. And then both of these will go through the same single lung models and the 2 architectures listed there to predict the density and extent for each side. So again, these models only predict 2 labels, but because I know which side is the right and which side is the left from my lung cropping model, I can then assign the laterality after the fact. And then I also had these whole image models where I just fed in the images. I used a size of, I think, 512 by 512 roughly for training. And then that model would predict 4 labels, density extent for each side. I averaged all of them together, then computed the mRALE score from those averages, and then rounded to the nearest integer to come up with the final prediction. And this is just some text explaining what I did for the inference. And so the final ensemble consisted of a total of 4 whole image models, 4 single lung models, and then 2 models for cropping the lungs. And as mentioned, predicting 4 and 2 labels for the whole and single lung models respectively. And these were the final results for the challenge. So for the validation, I achieved a quadratic weighted cap of 0.894, and on the test, there was a little bit of a decrease in that score, which was 0.884. And so thank you for listening to this solution. Again, thank you for the organizers and the annotators. This is my contact information if you have any questions. My plan is to have my code and models publicly released so people can see some of the finer details of the training process. And so look forward to that. Thank you very much.
Great, thank you, Ian. Next is Ron.
All right, let me share my screen. I think is this one. So can anybody see my screen? And
Yes, you're good.
Okay, yeah, okay, start. All right. So good afternoon, everyone. So my name is Ren. I'm very excited to be here to share my journey with the Midrich challenge. I'm currently an assistant professor at the Department of Radiology at UW Medicine. So before I begin, I would like to thank everybody from Midrich for hosting such a great event. And I'm very fortunate to have the chance to participate to the past two Midrich challenges in the past 2 years. So let me get started. So this slide summarizes my overall thought process for this challenge. And the first step is to understand the problem. So on day one, I asked myself, what would be the input, what would be the output, and how should I define or choose the loss function? And then the second step is to analyze the data. Do we have a big data set for training or a small data set? If a small data set, how should I pre-train the model? And additionally, how should I determine the training validation split such that I can have a metric to evaluate different model architectures? And after these two, the final step becomes very straightforward. It's all about selecting the best model architecture and performing the model ensemble. So let me go into more details of each step. For input, we have a few different options. We can use the full chest X-ray. We can use the cropped chest X-ray where we put a rectangular bounding box around the lungs. And we can also use the segmented lungs as the input. And for output, we know based on the definition of mRALE score, we know it's an integer between 0 and 24. So this potentially can be treated as a classification problem. But as Ian noted, it's important to recognize that these classes are ordinal because these they have the specific order. So an easier and much straightforward way would be just to treat it as a regression problem using the mean square laws. So based on my experience, the best performance is achieved by using the full chest X-ray as input, coupled with the mean square laws. And then we come to the data, which in my view is the most important piece of part for any model training. And most of us directly use or modify the existing models based on the trained on the ImageNet dataset. However, we have to realize that the ImageNet dataset has over 14 million images. So if you directly use this model to train on the training dataset that we have, which is about 2,000 images, it's probably not going to be a good idea. So therefore, almost everyone use some public chest X-ray dataset for pre-training. For example, the MIMIC, the NIH, the chest expert. But I think there's a few limitations with regarding to this challenge because these datasets are all pre-COVID, and also the disease classification is not very relevant to severity quantification, which was the task of this challenge. So as a result, I think some of the features learned in this pre-training process, if you use this public chest X-ray dataset, may not be helpful for this task. Therefore, I decided to further fine-tune this model with another public dataset. It's the BRICS dataset, which is a COVID chest X-ray dataset with manually annotated COVID risk scores. I will not go into more details about this dataset, but you can find more information here on this website. So essentially, it's a kind of a risk score for COVID patients, but this score is quite different actually from the mRALE score. It has a range from 0 to 18. So I just normalized the score to a range of between 0 and 1. I did the same thing for the mRALE score in the training process. And following these pre-training steps, I need to perform the final training using the Midrich dataset. So here, if I use a single train validation split, I think there's a few concerns. First one is, what if the validation set I selected is overly simple or overly challenging, which means they do not represent the population. So I think this is very likely due to the randomness of the sampling process. So as a result, the model that works well on this particular validation set may not work well on the test set. Therefore, when I evaluate the model, I always use cross-validation. Basically, I created 5 or 10 different train validation splits and trained 5 or 10 different models. So when I determine whether model A is better than model B, I evaluate the performance on all of the 5 or 10 validation sets instead of just one. And this also gives me the option to perform ensemble, even though each model is trained only with a subset of the training data, but with 5 or 10 models, that will pretty much cover the entire training data set. So now all the steps are clear and my workflow becomes very straightforward. First, I choose a model architecture and pre-train the model using the mimic data, and then followed by the break cell data. And then I fine-tune the model using the mRALE training data set. And so the task is to simply find or select some of the best models for the final ensemble. So I explored a few different options, including choosing the single best model architecture based on the performance on the 10 validation sets, or another way is for each validation set, I pick the best model architecture. So the final ensemble will be a mix of several different model architectures. And since I was using my personal computer for this challenge, it has a single 3090 GPU, I didn't have time to explore too many different model architectures. And in fact, I just used the two I used last year for the COVID-X challenge, which is EfficientNet and the swing transformer. So I explored a few different variations on the input size. And so basically, I think that's pretty much my entire thought process for the challenge. I think to summarize, the two keys for me are first to use proper data for pre-training when dealing with a small training data set. And second, to always use cross-validation and ensemble when selecting the models. And I forgot one more, which is equally important, and that's a good dose of luck. So thank you all for your time and open to any questions. Thank you.
Great, thank you, Ran. Very nice. I like that last conclusion. I think it's a useful thing for all of us.
Yeah, definitely.
Okay, so we'll save questions for the end, and then Finn, you'll be our third speaker.
Sure. I'll try to share my screen now. So I hope you can see my screen now. It should work.
Yes.
Perfect. So yes, I'm Finn from the University of Hamburg. I'm a PhD student in the topic of deep learning with medical images. And yeah, Alexander Schläfer is my supervisor. And this is the presentation of the third place solution, as we have seen the first two ones. And also I want to thank the challenge organizers for organizing this challenge. It's a lot of fun. And I think this really brings the field forward. So let's have a short recap about the last challenge, where we also participated and achieved also the third place. So here the goal was to predict a binary prediction if there's COVID or not in a chest X-ray. And the challenges were the image quality, because only portable AP images were used, and also a bit of noisy labels, because these COVID tests could have been like 2 days old or 10 days old, which would be the same result in the end. And therefore, we have a risk for overfitting, especially when using large deep learning models. And so what were the key points of the winning solutions? They were pre-training on large-scale data set, as also here in the first two solutions has been shown to be a good strategy for those challenges. And furthermore, the second place in this particular challenge used some specific pre-processing by cropping the images to the lung areas, which is also done by Ian. So coming to this challenge, now we have this mRALE score prediction where we have I will skip the details now because we have heard it. But in general, some challenges remain. The image quality is similar. We have, again, portable AP views. But now we have an ordinary regression task, which has also been mentioned by my colleagues before. And again, we have a slight class imbalance because we have a lot of 0 scores in comparison to the other scores. So again, we are likely to overfit if we use very big deep learning models. So what was our approach? In short, we did some manual data cleaning, used pre-trained models and large-scale datasets for pre-training, and also we used some more or less customized loss for this ordinary regression task. And in the end, we also did some ensembling and stochastic weight averaging, for example. So about the data. The used data sets were the Chexpert data set as a very large pre-training database. Then we used some COVID-X V9b, which is not the Midrich COVID-X data set, although they sound very similar. Then we used the COVID-X Midrich data set and the final challenge data set for the mRALE challenge. And we decided to use some data cleaning where we only use one image per patient and drop the remaining ones, and also manually remove some images of bad quality, and some examples are shown below. And for the model architectures, we decided to use the Swin transformer, where we actually stole the weights from Ran from the last challenge because they performed very well and he had a large data set which we were not able to access. And therefore, we decided to just use the weights and fine-tune them on the mRALE data, and this worked pretty well. Second, we took our own solution for the COVID-X challenge, and this was a ConfNext, where we again fine-tuned the weights on the mRALE data. And last but not least, we used a data-efficient version of a vision transformer, which has shown to be good for these X-ray classification tasks. And here we pre-trained this on the Chexpert dataset, followed by the COVID-X3 dataset, followed by the COVID-X dataset, and then we fine-tuned on the mRALE data. So a lot of pre-training here with a lot of different datasets. And coming to the training objective, as already has been mentioned, it is an ordinary regression task. So we have these scores from 0 to 24, which are ordered, and therefore we want to penalize higher deviations more than smaller ones, for example. So what can we use would be the mean absolute error or mean squared error, as it is done by the first two solutions. But also there's a possibility to get this problem into, or you cannot directly use cross-entropy losses here because then you would not pay attention to these orderings, but there are some versions of these losses where you would handle the labels as a ranking scheme, and then you could perform a multi-label classification. And this CORN loss, which stands for conditional ordinary regression for neural networks, does pretty much that, but it also adds some rank consistency, which means that a lower rank will have a higher score than the next rank, for example. I don't want to go too much into detail here. In the end, we used either the CORN loss or a combination of the MAE and the CORN loss for our final models. And we evaluated our models on a fixed held-out test set for general model comparisons, And then again, with the remaining data, we performed 5-fold cross-validation for hyperparameter tuning. And then our final submissions were the following. So the first submission was a combination, an ensemble from the Swin transformer and the convnext. And in each model, we had 5 different checkpoints from the cross-validation, which we also assembled. The second submission was exactly the same as the first submission, but now we use the held out test data in addition to the training data because we don't need it anymore after having compared our models. And the third submission was, again, the second submission, but now we added the data efficient vision transformer and also some stochastic weight averaging, which should help to improve the generalizability of our models, which is seen important for challenges. So coming to the results, you can see that overall, there's no big difference between the different submissions. Interestingly, adding the additional test data to the training set did not help. In fact, the score got decreased, and our first submission worked best. And overall, our findings are that data and data cleaning is very important for these challenges. We did not observe a clear best loss across all models, but we have seen that ensembling and also this stochastic weight averaging helped to improve the performance. So at this time, it's time to thank you for your attention. And again, thank you for organizing this challenge. I had a lot of fun, and I would be happy to see another challenge.
Great, thank you, Finn. Appreciate that. And I want to congratulate all 3 of you on placing in the top 3 of this challenge. And also thank all the people who participated. Obviously, we can't have winners unless we have participants. So everybody who gets into these challenges is really doing a great service for moving these things forward and helping these challenges be successful. Yeah, let's open up for questions. Siva?
Hey, good afternoon. This is Siva, and I have a question to Yan Pan regarding his model pre-training. So my question is, when you pre-train the model, so you're using huge models like efficient at B4 and convex models, how do you do this pre-training? Kind of, are you doing multiple stages of pre-training, like you are training the dense layers, then freezing, unfreezing the layers, or could you please explain in detail about how did you do this pre-training and how did you fine-tune these models?
Yeah, sure. So I basically started from ImageNet pre-trained weights, since there's a lot of publicly available pre-trained models on ImageNet. And then for the pre-training part, I basically just trained it with, I forgot exactly what parameters I used, but it's a little bit of a lower learning rate than you would typically use if you were training from scratch. I think something like, I think I used Atom W optimizer, and it was on the order of like 10 to the -4. And then I just trained for like 10 epochs. I don't bother freezing, you know, the earlier layers. We're doing multi-phase pre-training. The ImageNet pre-train weights are already pretty good. So it's just trying to adapt it a little more to chest radiography in particular. And then in order to fine tune on the competition data set, I lowered the learning rate a little bit further, I think on the order of like 10 to the -5. And then just trained, I think, for about like 10 epochs going through the whole training set. So it's pretty straightforward. And I found that generally you don't really have to do multiple stages of pre-training or freeze and unfreeze layers and all that kind of stuff. You can kind of just train end to end and then fine-tune end to end and usually achieve a good result.
Oh, that's great. So you just train at once. So you didn't bother freezing and you just train with a smaller learning rate starting from layer 1 to layer n. So you kind of fine-tune the entire model at one stage, right?
Correct.
Oh, that's great. Thank you very much.
Other questions? Sure, Ati.
Hi, so I have a question to Ransang. So my question is that in your training strategy, did you use any augmentations?
Yeah, so in the training, I use some very simple augmentations, for example, rotation within the 30-degree and flip horizontal. I think that's, there's some others like contrast adjustment or brightness adjustment, but with a small range. So pretty much that's all the augmentation I used.
Great. And did you use model ensembling for your submissions?
Yes, so always use the model ensembling.
And
So
how
I try
many?
to, I'm not sure which one of my submissions got the highest score, but I think it's 2 of them are 6 ensembles and the other one might be 10. So just depends on how many cross validations I have, whether I choose the top 6 models or choose the one for each validation. So something between 6 and 10, I guess.
Thank you.
Thanks.
And that's a good point for all participants. We'll make sure we get back to you, Ran, with the submission of yours that achieved the highest. So you can know the parameters that ended up being the best combination.
Okay. Yeah, thanks. To me, I think they're all the same. Actually, it's not that different, but yeah.
Other questions? Karen.
Yes, well, I'm one of the organizers for people who don't know me. So I just wanted to have a comment about the performances. Yes, we will give you all, which model performed best. We also have 95% confidence intervals of all your performance metrics. So you get, and like a lot of these performances were very similar, right? For this challenge, it wasn't required that there be a statistically significant difference between number 1 and number 2. But obviously that's something we will be looking into, and we will also be writing a manuscript with, with all of you, I guess. So I'm looking forward to that.
Yeah, thanks, Karen. I just was going to add as well that, we thought with this Midrich challenge number 2, with over 2,000 training and validation cases, which is more than we've had before, that we were providing a really good resource for training. But all of you clearly used training sets that went well beyond what we offered you. And our training set became maybe the 3rd, maybe even the 4th level of training for your systems, which I think is interesting. Did anybody try to use just our training set alone initially? And if you did, what was your performance at that stage with those training cases?
Yeah, I tried to train on the composition data set on its own, and it was honestly pretty close to what I got without pre-training. I think it was maybe like 0.01 to 0.015 off in terms of the final quadratic Wittig kappa. But I think for the purposes of competition, when sometimes you win by like 0.001, I had to just go with the pre-trained models.
Yeah, I guess that's the statistical luck part, is winning by 0.001, right?
Yeah, I think same experience for me. I think there's a 0.01 difference if I don't use any pre-training, just use the training data.
That's pretty interesting. Yeah, thanks for that. Lubomir.
Yeah, I'm also one of the organizers, but I have a question for Ian and probably for the other participants too. Ian, do you think your medical background was important actually? I mean, for the entire process of training and prepare the models and everything actually?
Yeah, no, that's a question to which my answer has changed over the years. So I think, once you have a pretty well-defined problem and well-annotated data, it's really more my data science skills that are useful in helping me win. But I would say that, if I want to think about a problem that I think is going to be useful clinically or to radiologists and all of that, then I think my medical background definitely comes in handy. sort of in the beginning when you're trying to define the task, the right metric, how you're going to annotate the data, what kind of data you're going to use. But for competitions, I think it comes down mostly to your technical skills.
But eventually you're deciding which images to keep for training and which you not. I mean, for your model, and potentially this one may make a difference. You can have maybe a little bit more cleaner, higher quality data.
Yeah, maybe a little bit. But I think some of the other competitors showed examples of poor quality data. So I think if you just take a look at the data, you'll get a sense of sort of what images look okay and what don't, even without a radiology background. So I will admit that for more complicated studies, for example, it may certainly be more challenging for someone who doesn't spend a lot of time looking at radiology images to figure out, what's good and what's not, like, multi-sequence MRI and stuff like that.
You're great. Thanks very much.
Before I call on Siva, maybe a follow-up for you, Ian, and the other Finn and Ran as well. One of the things we thought about doing as organizers was to go through the cases and choose just a single image that we felt was the best quality or we felt was the most clinically relevant. We didn't do that in part because of time, but also in part because we felt that having that collection of images for each case might be useful for your algorithms in ways that we couldn't predict. So we didn't want to remove information, remove data from your ability to train your models. Any comments on that? Do you feel you would have been served by having a single image, or did you find that you were able to in some way make use of the multiple instances of images in each case?
Yeah, so initially I trained on all the images because I didn't think that filtering them would do any good. But actually, when I filtered it down to just one image per study, I did get a pretty significant boost in performance on the validation set, like 0.0, 0.05 or something like that, which may or may not have been the difference between first and second place, honestly. So would it have been helpful? I think maybe to people who did not filter the images. But personally, I kind of like it when you kind of give a little bit noisier data or you don't do as much data curation, because to your point, it does sort of allow the competitors to then experiment with different approaches and see what works best, because it totally could have been a case that filtering did nothing or actually made things worse. So.
Yeah, Ran or Finn, any comments from that perspective from you?
I got similar results, like manually filtering helped. And also maybe for the question before, I had some difficulties in deciding which image to take and which to drop off. I mean, some were just different windowings or something like that. They were pretty easy to detect, but for some it was really hard to see which one would be better. And in the end, I decided to drop the other images because in the test set, you said that there will only be one filtered image per patient. So that is why the model did not need to be very generalizable to different post-filtering, for example. So that's why I decided to not keep them in the training data.
So I don't think keeping one image per patient is necessary for training, because we're applying augmentation anyway. So we create multiple instances of one image based on by doing rotation and some contrast adjustment anyway. So I don't think it's necessary to keep one chest X-ray per patient. But I do think that manually removing those images with a very high enhanced contrast is helpful, because I think that somehow reduces your bias of the model, because some patients may have those high contrast or enhanced contrast images, but others may not. So that will create some bias for the model training. I think that should be the key.
Great, all good points. Thanks for that advice. Another question from Siva.
Yeah, so I have a question for Ran Zhang. Your idea about using multiple models and training these models for each validation set and then trying to do an ensemble of the best model for each validation set is really impressive, actually. But you also mentioned about using multiple image resolutions like 480, 224, and 384. So if I'm getting it right, are you kind of training the model at each resolution for each validation set and then choosing the best model with the best resolution for that set? Or how do you pick that model for that given validation set?
Okay, thanks for that. I don't have a lot of time to try different input sizes for the same model. So actually I use 480 for efficient net, and I tried two different versions for swing transformer. One's 224, the other is 384. And honestly, I don't think the results changed that much. So yeah, but because for this task of severity quantification based on the opacity, I don't think the spatial resolution matters that much, because we're not focusing on some small lesions. We're not focusing on the some patterns of the lung. So I don't think the image size should be greater than 512 or 1024. So I just use this standard image sizes actually based on the ImageNet model that they are pre-trained on. So that hopefully that explains.
That's awesome. And I have another question. This is for all the participants. My question is regarding the batch size. So basically, do you observe any correlation between the image resolution and the batch size? For example, increasing resolution with increasing batch size, or increasing resolution with a decreasing batch size. So what is the effect of batch size on your model pre-training and fine-tuning?
Maybe I can start. So basically, I think the batch size is a bit set by the image resolution, because you can't fit too large batch sizes. If you have like 1024 resolutions of images, then your batch size will be like 8, I don't know, at best. But I personally, I did not really experiment with the batch size this time. I fixed it to, I think, either 46 or 128.
Okay, thank you very much.
Yes, CG.
Yeah, thanks. So first, congratulations on those top solutions. I have a question about the pre-processing steps. So I know Ian has mentioned like cropping with the bounding box with the pre-trained models, but I'm curious, like, have you guys done any pre-processing about the pixel values, like normalize the pixel value to like 0 to 1 or so? Because when I went through the data set, I noticed that the pixel value range can be very different. Like some are from like 4,000 to 6,000, and some are like 8,000 to 12,000. And also there's some like pixel value outliers, like due to the labeling of those, like it's a AP position like that. And also there can be different paddings to these images, some like zero padding and some like padding with some gray pixels. So I'm just curious, have you guys done any of this processing about this pixel value normalization? Thank you.
So I use this function in PyDICOM called apply VOILUT. It basically applies the lookup table as specified in the DICOM metadata. And then I will rescale all the values to 0 and 1, convert it to an 8-bit image. So now everything is between 0 and 255. And then for the model training, I will convert it to a range of -1 to 1. That's just sort of my personal preference, is to do the kind of like inception style normalization for training. But in brief, sort of apply that function, convert to 0 to 1, convert to 0 to 255 8-bit, and then convert to -1 to 1.
Thank you.
Yeah, I pretty much did the same thing, except for the last step. I keep everything between 0 and 1 instead of -1 to 1, but all the others are the same.
So before you normalize those to 0 to 1, did you do like a thresholding to remove those outliers, or just like minus the the minimum value and then divide by the range between the maximum and minimum value.
So I also look for the window level and window width information from the DICOM header, and using that to normalize everything and pixel value to 0 and 1. Gotcha. If there's no window level or window width information, I just use the minimum and maximum value.
That's great. Thank you.
Yeah. Thanks.
Other questions? So I have a question for the three of you, anybody else on the call who participated, and anybody else on the call who's just listening has experience. When we first began talking, when the working group on grand challenges first began talking about these results, we were surprised a little bit at the high performance that was achieved, especially in the context of this maybe being a tricky clinical task to assign these values, or to assign the extent and the density, and then convert that into a numeric value, into this pseudo, numeric quantitative, cumulative score of mRALE. And given the variability of the annotators who provided the reference standard for both the test set and our training and validation sets, given that inherent variability, it could be supposed that the ratings could be all over the place in a certain sense with regard to the raters, the mRALE score, and the images that were presented to them. And given on top of that, that all of you used other data sets to do initial training, which were likely to be not portable radiographs, for example, obviously annotated by other people. So is there any way to account conceptually for how you all achieved the high scores you achieved, given that underlying level of variability and clinical complexity?
So as someone who's used like quadratic weighted cap in the past, I think the absolute value of the metric is a little bit inflated relative to what you sort of actually see if you were to use another metric. So what I mean by that is it's like almost 0.9. It's like 0.88, right? And so it seems like it's very good, but if you like computed like a different metric, it might not be as good, because I think when I've done it, for example, for like diabetic retinopathy, I also achieve like pretty high QWK scores and like the high 0.8s. But if you compute like a different score, if you look at the accuracy or something like that, it's actually not quite as impressive. So I think that's one part of it. And then the other part might be, I don't remember exactly what the distribution of the data was, but if more of it was sort of clustered in the lower numbers, that would also help, because really it's when you have large differences between like the label and the prediction that it's going to throw off the QWK. But if most of them are kind of clustered in the lower numbers, then the differences are probably not going to be that big, if that makes sense.
Yeah, sure. Great points.
Yeah, I totally agree with Ian. I think if you use right now we're using quadratic weighted kappa, but if you're using a linear weighted or a non-weighted, the number may not look that good. But on the other hand, I think it doesn't matter that much if, for example, the score prediction is 4, but the ground truth is 3 or 5. So I think that in that case, I agree that the quadratic weighted kappa is a good metric for this type of task. I don't know if anybody else thinks.
Yeah, good. Thanks.
I think it's hard to interpret, to be honest, like this value between 0 and 1. And I sometimes looked at the mean absolute error just, and it was always about like 3. So there's quite a gap between the prediction and the ground truth, actually, if we have a mean absolute error of 3. I don't know what about the other participants, what they achieved in mean absolute error, but I think having similar to the others, having the high Cohen kappa might not result in perfect predictions in the end.
Well, good. Well, thank you for that assessment of that metric. Lumir?
Yeah, I have also a question to all three of you. How much time did it take to build the models, actually? did you work, completely from the very beginning of the announcement of the challenge, or somehow was it very intense kind of work during that time, or you not immediately, something like that? Okay, guys, who is going to start first?
Yeah, maybe I'll start.
Sure.
So I think as long as you have the data figured out, what data to use for pre-training, what data to use for final training, and what training validation splits are going to use, the rest of the stuff is pretty straightforward, actually. I'm using the libraries in the torch region. So they have the ImageNet pre-trained models. So you don't need to modify a lot of things, pretty much just change the classifier, because we're not going to change the feature extractor. So in terms of like how much time you need to put into coding and stuff, there's actually not a lot. You don't need a lot of time effort to put into that. So I think the key is to have the data in hand and knowing a metric that can help you to choose the best model, and just the rest is just to try a few different models.
Yeah, I agree. I joined a little bit later in the competition, but I have participated in a lot of these types of competitions in the past. And so I kind of built up a code base already to do a lot of experimentation. So I basically just came up with a plan and decided I was going to just try all these things. And in this case, it happened to work out well. There are other times where it doesn't work out well. And so I think to Rand's point, once you kind of have a vision of what you're going to do, and you already have sort of the training code and stuff in place, it doesn't take that much to experiment or to generate additional experiments, other than the fact that you're limited by your computing resources. And though while I'm at work, I always have like ideas in the back of my mind. So it does serve as like a distraction from my actual work during the day. But in terms of like how much intense time I spend on it, it's usually more so in the beginning. And then once everything's set up, everything becomes much easier down the road.
Great.
Okay.
Actually,
Finn,
same.
yeah.
Okay.
Yeah, same applies to me. So, but basically I had some ideas, and unfortunately most of them did not work. And these ideas are pretty time consuming, but also as a PhD student, I think you have to do some experiments, so it's worth it. But yeah, in the end, if you have a pipeline, if you have the data, you can pretty much use the given models, and they seem to work pretty well, especially for this task.
Great, thanks very much.
Yeah, thanks. Siva.
Yeah, so I have this question for all three of you. So considering the case where you use full chest X-ray images to train your models and then measure the mRALE score, and you get a pretty good match of the mRALE compared to the ground truth, how do you even, how do you even interpret, or how do you even make sure that this mRALE score is because of the result of the edema in the lung? So if there is a possibility of seeing the edema-like manifestations in some regions outside the lungs, and if still you're getting a good mRALE score, just not because of you seeing this edema manifestation inside the lungs, but something outside the lungs. So have you gone that extra step to interpret the decision of your model as to why this mRALE is matching the ground truth, and why, how do you even localize, how do you interpret this decision as far as a given input is concerned?
I mean, yeah, that's a great question, and a question that I think plagues a lot of deep learning problems. To be totally honest, during the course of a competition, I don't really try and do all of that. And if I were to notice something like that, which I could exploit to get a higher score, then I would totally do that. And then I usually save the interpretation stuff for after the competition, when I'm not as concerned about whatever score I'm getting. But to your point, you know, I did look at the performance. Sorry, there's like an alarm going in the hospital. And the performance between the single lung models and the whole image models were not that different. So presumably we can assume that they may be looking at similar things.
Yeah, that's great, because in Ian Pan's model, where he was segmenting them, the model into, cropping them into right and left lungs, there is a lesser probability of including the noisy pixels or regions outside the lungs. So there is a little bit chance of including those noisy regions, but when considering the entire image, there is still a possibility of having lots of false positives that may still contribute to the mRALE score. And that's why I just want to know, how do we even make sure that the mRALE is because of the edema signs within the lungs and not something outside the lungs? Yeah, thank you very much.
Any other questions? Okay, so let me end with one final comment and one final question. The comment is, actually, I guess two comments. Finn, I appreciated your reference to fun at the end of your presentation. This is all about, it's meant to be fun. These challenges are meant to be conducted in the spirit of fun, open science, and really trying to move the field forward, but move individual groups forward with their ability to approach these problems in a unique way with the clinical data we're able to provide as a background. And then along the lines of open science, I was really struck by all of you, how you all used other open science tools that are already out there, other data archives from other groups that are publicly available. And Finn, I think you even mentioned that you used Rand's weights from the first COVID Midrich challenge. And so I think that's amazing. I think that really is true to the spirit of what we're trying to achieve here. So well done to all of you for pursuing things in that vein. That was my final comment. And then the question was, we need not answer it here, but if any of you on the call, the three of you or others who participated in this challenge or touched the data in some way, if there's some way, knowing what you know now, that you could help us, if we were to do this challenge over again, the same exact challenge over again, what advice would you have for us? This could be offline if you want, to make it easier or more accessible or more something for you as you develop your methods that will help us kind of guide the conduct of our future challenges. So with that, on behalf of the organizing group, Karen, Lumir, Ben, Emily, I want to thank all of you for participating in the Zoom call. Thanks to the three of you for first of all achieving the high performance and your willingness to share your methods with our group, and all the other participants who made the challenge possible. Thank you very much.
Thank you.
Thank you.